In topic 6, we're going to be discussing exponential functions and their properties and how they're used to represent real-world problems. We spent a lot of semester 1 discussing lines, which are nice constant growth functions, but exponential functions we'll find will grow a lot quicker and have a few unique properties to their graphs. So when it comes to exponential functions, we're going to have to be sure we understand the properties of exponents. So exponents are those powers, those raised up powers above a number. Now, each of these rules that you'll see down here, you may have seen before, but oftentimes students need to be reminded of them. So let's look at a couple examples here. Whenever you have two like bases, these are both x's, and they have an exponent, these powers, you could think of this x to the third as x times x times x, and x to the fourth as x times x times x times x. Instead of writing those all expanded, we can rewrite them with one common exponent. So our power would be x to the seventh. Now instead of having to write these all out and count them, what could we do with these two powers up top? When we multiply like bases, we add those exponents. So we could have just said 3 plus 4 is 7. That's a little confusing when you say, well, aren't we multiplying? It's the exponents we add when we're multiplying like bases. When it comes to taking a power to another power, notice how we have this x to the third, and that entire thing is being squared. That's like taking x to the third times x to the third. Now we could apply the rule we had with the product of powers. So I'd have 3 x's in the first term and 3 in the second. That would give me a total of 6. But instead of having to write it out and expanding it like any of these, I could just have taken 3 times 2. So now we are multiplying the exponents when we have a base with an exponent to another exponent. If we happen to have a coefficient or a number inside being taken to a power, 3x to the fourth says we're taking 3x times 3x times 3x times 3x. We would have to multiply all the 3 times 3 times 3 times 3. And that would give us 81. X times x times x times x. There would be 4 of them total, so our power would be 4. That's why when we have a product, something already multiplied inside being taken to a power, we expand it or we distribute that exponent into both of them. Now distribute means each of them gets it. So 3 would be to the fourth power. That's why we had 4 3's being multiplied. And x is to the fourth power. On division or quotient of a powers, if we were to expand it, we would have 7 x is on the top of the numerator and 5 in the bottom. We know that if you took 5 divided by 5, it would make 1. It would reduce to 1. So x divided by x is also 1, times also 1, times also 1, also 1, also 1. We'd be left with 2 extra x's, and we would say x times x makes x squared. Now, since they're left on top, we would leave it like this. We could write it over 1, because all of these were 1's, or we could simply write x squared. If you didn't want to write those all out, think about your 7 and your 5. What could we have done with those numbers to get us the 2? Well, we would subtract. So in your packet, you may want to try some of these extra practice problems to practice exponents. Because from the word exponents, we're going to gather our exponential function, which is the focus of this chapter. One other type of exponent you might encounter is a negative exponent. 4 to the negative 1 actually is 1/4. It is not negative 4. Or 2 to the negative 3. We still want to know what 2 times 2 times 2 is, because that's what 2 to the third would be, and that's going to be 8. But since it has this negative in there, it places it in the reciprocal place, or the denominator in this case. So 1/8 is our answer, not any of these. These are common mistakes that students might make. Negative exponents change the location in terms of the numerator or denominator of what's being taken to the negative exponent. You'll have more practice with these in your packet. Finally, whenever you have a number to an exponent that is rational, one thing is rational means like a fraction or a ratio. So it's a fraction. These are powers with fractions, and they make square roots, or any kind of root really. So when we say 9 to the half, I like to remember this phrase. You have the power over the root. This is my power of 9, so I'd want 9 to the first power. And this is my root that I want to take. I want to take the square root. Well, 9 to the first power is 9. So the square root of 9, that means what times itself makes 9? That'd be 3. If you ever had 64 to the 1/3, my power is 1. My root is 3. Of course, 64 doesn't change, but what times itself makes 64? That's 4. And that's because 4 times 4 times 4 is 64. Just a fun little fact here. What if we combined our last slide with negative and a fractional rational exponent? This would be 1 over 5 to the half, because that negative will change the part of the fraction that this 5 is in, and the half stays, but we now know that that is the 5 to the first power, which I don't have to write, but I will, and the square root. You can put your 2 here, but if you don't want to, anytime you put that root symbol, it's assumed to be a square root. Now down the road in your future math classes, they may find that you want to reduce this and not leave a radical in the denominator, but for now, we'll leave it. We want to remember that if you have a fractional exponent, the power is on top, the root is in the denominator.